Okay, shall we start?
Yeah, we can start.
Okay, thank you very much. Well, welcome everybody to this session 2B of the Transit Data Conference. We're very happy to have the possibility of having this conference in this format, but we couldn't do this in person this year, but hope we can come back to in-person conferences in some time, but for now, this is great that we can hear each other through this platform. My name is Marcela Munizaga. I am a professor at the Civil Engineering Department at Universidad de Chile. I'm talking to you from Santiago, Chile. And as I said, very happy to be here. This afternoon, we have a very interesting session about operator performance and operations applications. We have speakers from the transit authorities and also from universities dealing with different aspects of operations of our public transport systems. For the attendants, you know that you can ask questions through the questions and answers document that has been, the link has been posted in our chat. So please feel free to paste questions there to the panelists at any time. And the questions will be answered through the same systems, through the same platform. Well, to begin, we have a presentation called Performance Chauffeur, a standardized metric on drivers' operational performance based on peers' performance, a methodological framework developed at Société de Transport de Laval, presented by Grzegorz Wielinski from Société de Transport de Laval.
Thank you, Marcela.
You can share your screen now.
I'm trying to do. Do you see my screen now?
Yes, we can.
Is my presentation in full screen? Marcela?
Yes.
Is my presentation in full screen, yeah?
It is in full screen.
Okay, great. So, hi everyone, thank you for having me here. I'm Grzegorz Wielinski. I'm currently a data scientist at Société de Transport de Laval. I'm here on behalf of our team who participate in a project, Performance Chauffeur. Performance Chauffeur looks to create a standardized matrix on drivers' operational performance based on peers' performance. And just before beginning, I just wanted to know that Vincent is also a key contributor for this project. So who are we? The STL, the Société de Transport de Laval. I'm working the XDM team, or the Big Data Evaluation team. The Big Data Evaluation team at the STL is comprised of multiple data scientists and data analysts with multiple backgrounds. We are a transit agency operating in the North Shore of Montreal, the city of Laval, with a population of 400,000 inhabitants, 20 million annual ridership, 46 bus lines, and 600 drivers. So now on the project itself, we wanted to use our numerous passive data streams and assess a driver operational performance. And usually one indicator used by transit agency is the driver's on-time performance. So for example, here our driver, let's call it John, and we compare its on-time performance amongst all of its peers. So each one of them is assigned a score depending if they are able to be on time or not. But now if we compare John to Mark, which one is the better driver? Is John with an 89% on-time rate or Mark with a 76% on-time rate? At first, we could say it would be John, but now if I tell you that John is working on evening weekends, while Mark is working on weekdays, mostly in rush hour conditions, did it change your mind? So the traditional way to compare our drivers cannot fully answer the question because it induces some bias, and the bias is because it doesn't consider the driver operational context. It could come from the time of the day where they're operating, the weather conditions, and the congestions, and it's clear that those factors are affecting the ability of the driver to respect its schedule or its performance. So performance Chauffeur looks to develop a new methodology, a new framework to standardize those metrics by sampling drivers working in similar operating conditions. So now, instead of comparing John to all of its peers, we compare John only to peers who perform or operated in the same or similar condition than him. So now we can update those scores to better reflect the reality. We created 3 standardized metrics. The first one is the travel time, so the ability to respect travel times. The second one is the speed, so the ability to respect speed limits. Then the deceleration, so the ability to gently brake, or the general comfort in the bus. So for each of those metrics, we created a score. So a driver has 3 scores, one for travel time, speed, and deceleration. And then we aggregate those scores to create one unique score for the driver. And we do this manipulations each week. Because over time, if we do this, we can track those metrics to see if the driver has improved or not. And to ease these improvement, we develop a dashboard. The dashboard can help us to do so. So for operation, this project is really useful because this eases their managerial duties, mostly done by their supervisors. And it helps supervisors to reward drivers who perform greatly. And for our planning department, we wish that the scores generated by this method could improve our travel time planning. So mainly by filtering only drivers who perform in average or standard scores, standard drivers performing to better schedule our planning. On literature, we found a lot of tools from vendors in the market to assess the driver's performance, mostly onboard equipment, but none of them really use the notion of comparison between peers to create a true score of the operational performance. We found only one paper underlying another framework to assess the standardized metric. So that was what made us to start this project. So here's the proposed framework. We have multiple data sets, so the bus operated trips, GPS data, some shape files like the speed limits. We do some basic data cleaning, outlier detection, map matching. But the key here is the peer sampling process. So for each trip operated by the driver, we try to find 50 other trips operated by other drivers to compare this trip with its peers, but only with peers that operated in the same conditions as him. And then we developed 3 specific algorithms to create our specific scores. And finally, we create our main score, which is the aggregation of the 3 scores. So in conclusion, what we wanted to do, we wanted to create a standardized metric to help assess the bus drivers' operational performance without bias, or by reducing as much as we could the bias. To do so, we work closely with the operation department to have their direct feedback. Because of COVID, the integration, or mostly the implementation of the solution with the operation team didn't go through as planned. And finally, we developed also a dashboard, which is quite comprehensive. Here's a little snippet of it. It's only one dashboard from multiple sheets that we have. But you can understand the fundamentals. We can select a driver, see its evolution over time. In this case, is the travel time score. We have some stats of other peers who work in the same condition as him. You can go as precisely as by selecting a specific line to see scores and map, etc. Thank you very much.
Thank you very much, Gregory. That was perfectly on time. Thank you very much for your presentation. We will now listen to the second presentation of this afternoon. The work is called Using Aggregate Operator Data to Improve Extraboard Planning. This work is by Wang, Koutsopoulos, and Nigel Wilson from the Massachusetts Institute of Technology, and will be presented by Wang. Please share your screen.
Okay.
Perfect.
Okay, hello everyone. Today I'm going to talk about my project on using aggregate operator data to improve the extraboard planning process. So before I start, I just wanted to say that the Extraboard workforce is what the transit agency hires to cover unexpected situations such as operator absences. And the goal with operator absences usually at around 15% of the total scheduled services at the MBTA, it is very important to improve the Extraboard planning process to reduce lost service, overtime, and cost. So breaking it down into smaller objectives, the first is to mine relevant data from HASIS Daily, which is a scheduling software used at the MBTA and for the rostering and the scheduling of the operators. So after that, we want to characterize and model absences, overtime, and lost service, and using such models to develop the Extraboard scheduling methods. So this is the decision-making framework that I'm using here. On the demand side, we have absences, extra service, and unexpected situations to create the need for operator hours, noted as open work. And on the supply side, we have two sources. The first is the dedicated Extraboard workforce, and the second source is to asking the regular operators to work additional time, so overtime. So these two sources form the total available time to cover, and the demand and supply of operator hours interact to reduce the trip outcomes. So in this project, we want to estimate the amount of open work and also the overtime availability and schedule the Extraboard operators to optimize for the trip outcomes. So there are two categories of model that to achieve this goal we want to develop. The first is the absence models, and the second is the scheduling model. So for the absence models, we use the variation of count models, a negative binomial regression at the aggregate level. And the potential variables that we have tested include the time of day characteristics and also historical absences, overtime, and lost service. So the second part is the scheduling model. It is a multi-period integer optimization problem. So multi-period means first the tactical level, which we want to decide the number of Extraboard operators scheduled for each day of the week. And on the operational level, we want to determine the report times of such operators to match with the demand for operator hours. So running these models, the key findings of the absence models include, first, no significant relationship was found with historical quantities on absence, overtime, and lost service. So the resulting model mainly reflects the average behavior for the day of the week. And looking on the right-hand side, we see that the unexpected absence rates actually varies from 0% to 20%. So quite a wide range. So there are quite a bit of unexplained variations in there. And it is a quite difficult task. So compared to taking an average of the whole rating, this model improves the mean absolute percentage error by 6 to 9%. And we're still left with around 20 to 25% mean absolute percentage error among the 4 rating/garages that we've tested our model on. So with the scheduling model, we had 2 formulations. The first is a deterministic formulation, which we assume no uncertainty in the absences or overtime availability. And the robust formulations assume that the absence and available overtime fall into some uncertainty set. So we account for our modeling errors in the robust formulation. And in terms of the evaluation scenarios, we have 2 scenarios as well. The first is a constraint resource. So we limit our resource level, that is the staffing level, to what we have observed the agency has hired in that rating. And in the unconstrained case, we remove that constraint to let the model tell us what the optimal staffing level is according to our modeling assumptions. So for the constraint model with the current level, we have found very similar assignment strategies because the Extraboard operators are limited and we can only cover the most basic needs. So if we remove that constraints, different modeling strategies give very different results. So looking at the graph on the right, we see that the more robust models give significantly more operators to cover for unexpected situations. And they, in terms of the results, they achieve more stable results with less variance. And the nominal models, so the deterministic models, overfit to their situations or overfit to their inputs. So if the realized outcome is the same with what we have modeled, then it will do well. And then if the realized outcome is different from what we have modeled, then the results will be worse compared to the robust ones. So just to conclude, the lessons learned from this is first, absence and overtime contain a lot of noise, and more and richer data is needed to revisit this problem. And the robust scheduling models do not necessarily achieve lower costs. They're generally more conservative, prefer the fixed cost of hiring more operators to the variable cost of lost service and overtime. So when we compare our model results with the current assignment performance metrics, we found that there are quite a few inconsistencies because of the data keeping issues. So I think that we think that with a more consistent, reliable record keeping is needed for the model results to be comparable with the observed results. And lastly, one limitation of this optimization model is that the garage dispatcher usually makes a lot of real-time on-the-fly adjustment decisions that are not necessarily reflected in the optimization model. And yeah, that's it. Thank you.
Thank you very much, Qing. Again, perfectly on time, so we're doing good. I remind all the participants that you can place your questions at the document, which link has been shared through the chat. Our third presentation today is called Two-Way Adaptive Transit Signal Priority for High Frequency Bus Lines Using Deep Reinforcement Learning by Wenxun Hu and Amer Shalaby from the University of Toronto, and Wenxun Hu is presenting. You can share your screen now.
Thank you.
Can you put it in presentation mode? Yes, perfect.
Yeah. Okay. So good afternoon, everyone. I'm Wenxun, and I'll be presenting our work on a two-way adaptive transit signal priority, TSP, designed for high-frequency bus lines using deep reinforcement learning. Well, the objective of this study is to develop a strategy that optimizes jointly reliability and travel time of buses coming from opposite directions. So we emphasize reliability and travel time because they're two key indicators of transit service quality. We know that uneven headways like long headways result in crowdedness at bus stops. Short headways lead to bunching. So passengers travel on bus lines with irregular headways experience excessive waiting time, which increases out-of-vehicle travel time. Well, the in-vehicle travel time is increased because of transit delays, and a great portion of which can be attributed to traffic light. So we want to use TSP to improve these two objectives. So the method we are using is deep reinforcement learning, a machine learning approach. So in general, a reinforcement learning agent learns the best policy via its interaction with the environment. So we use AIMSUN to simulate a transportation network. So this network is built using real-world data, such as automated vehicle location data, ride checks, and traffic data. Then the agent is the TSP control system, which observes environment state. Whenever a bus arrives at an intersection, we collect state of the environment, which includes headway and traffic flow, and also signal timing. So the agent perceives the state and chooses an action of whether to extend the green phase or truncate the green phase. Then action has been executed by AIMSUN, and after the action's been executed, the agent received a reward from the environment, which tells the quality of the action that has been taken. So the reward is calculated as a function of headway improvement and travel time. So our agent gains experience with every approaching bus and ultimately knows the best action that would optimize transit headway and travel time in all different scenarios. So the TSP algorithm contains two deep reinforcement learning models, one initialized for each direction. So these two models are trained through interaction with AIMSUN and the coordination algorithm. When there are buses in both directions, the coordination algorithm is called to generate the optimal action for both directions. So after the two models converge, we got two trained models together with the coordination algorithm can generate the best action. So and these two models can continue to learn in the field after deployment. So this slide, we compare the benefit of using our two-way TSP versus conventional TSP, like what we are using in Toronto, which is an unconditional transit signal priority. In the first scenario, when both buses are late, two TSPs do the same to expedite buses. When both buses are early, then the conventional TSP would expedite the bus, which reduces travel time, but then increase the headway deviation. However, when both buses are early, the two-way TSP offers an opportunity to hold two buses, which improves the headway deviation. In the second case, when both buses are late, then the conventional TSP and two-way TSP do the same thing. They expedite buses in both directions, which improves headway deviation. When one bus is early and the other is late, expedition would improve the headway performance of the late one, but aggravate the headway deviation of the early one. So the two-way TSP instead tries to find a balanced and optimal solution that considers the overall improvement in both directions. The two-way TSP algorithm is trained and tested at an intersection in Toronto using AIM microsimulation. So this slide shows the reliability and travel time performance of two-way TSP and three baseline scenarios. Dark blue shows eastbound performance, and the lighter blue shows westbound performance. No TSP is that we use background signal timing without TSP, and Toronto is that we use background signal timing with Toronto's current TSP. And first come, first served algorithm is very similar to our two-way TSP, but instead of using a coordination algorithm, we use a first come, first served algorithm instead to prioritize whichever direction that has a bus coming earlier than the other one. The coefficient of variation, CVH, is used as a measure of reliability, which indicates headway adherence. So in short, the two-way TSP has the lowest checkout coefficient of variation of headway in both directions that indicates the best headway adherence. And then the figure on the right shows the average travel time. The two-way TSP provides huge savings when compared with no TSP, which is about 24% lower than without TSP. However, its travel time is not the lowest, but pretty much comparable to Toronto's current TSP. So we know that reliability is sometimes considered more important than speed, and that is the reason why our TSP algorithm addresses transit reliability. And also that is the reason why it is worth trading a small percentage of travel time for headway improvement. So the two-way TSP is designed for a single intersection. However, trying to restore headway at one single intersection may not be practical. So future research can develop route-level TSP to enhance the benefits and considering, for example, using multi-agent reinforcement learning. And also the two-way TSP presented used loop detectors, which largely restrict the types of data that we could use. To improve the performance, we consider using more advanced connected vehicle technologies to provide richer data, such as real-time bus tracking data, passenger loads, dwell time, and also enables communication between the infrastructures and also between the infrastructures and transit vehicles. Yeah, and that is the end of my presentation. Thank you.
Thank you very much. Very interesting presentation. We will now move to our fourth presentation this afternoon, which is called Empirical Identification of Location-Specific Carbon Monoxide Patterns using a low-cost sensor mounted on a transit bus in operational service. This work is by McCord, Rabi Mishalani, Andrew May, and Yangyang from Ohio State University, and will be presented by McCord. Mark.
Thank you, Marcela. Am I on? Can you see the screen?
We can see your screen.
Great, thank you. And good afternoon, everyone from Columbus, Ohio. Rabi and Mishalani and I have developed the Ohio State University campus into a living transit laboratory in which we like to conduct research to improve transit operations. But we also like to look for novel uses of the bus platform. So in this study, we teamed up with Andy May and Yangyang Zhu, two environmental researchers, to put a low-cost carbon monoxide sensor on the roof of a bus, let it go around in operational service and see if we could look at location-specific, if we could detect location-specific readings. The motivation is, in an urban area presently, air quality is monitored by spatially dispersed air quality sensors, and they're so far apart that you can't pick up the spatial variability across the urban area. So we came up with the idea of putting a low-cost sensor on a transit bus that's in regular transit operations. The idea being that the repeated regular service coverage by a transit bus would give enough sufficient independent observations to pick up underlying spatial patterns. So in this study, we mounted a sensor on the roof of an Ohio State University bus, let the bus run its normal transit operations, got the data from our sensor, and looked for spatial patterns in the data. We used off-the-shelf components. In this study, we're only interested in the carbon monoxide sensor. We configured this sensing configuration, put it in acrylic housing with air holes to let air pass and water seep out, and mounted the entire package on the roof of Ohio State University bus 1105. I note that our long-standing relations with the managers of OSU transit service allowed us to do this. I don't think there'd be too many transit agencies that would allow us to have drilled holes in the roof of their bus for experimental research, but we're grateful to OSU for letting us do that. While bus 1105 was doing its normal transit service on the West Campus route, we collected data over 5 weekdays in October 2017. The West Campus route at the time of the study carried about 1,000 passengers per weekday, had a 30-minute cycle time, so we get about 2 bus trips per hour. It would serve a large park and ride facility in the west of campus, travel to the main part of campus, go down to a large and condensed medical center, and go back to West Campus. Go on arterials and local streets, but notably it would pass under, where is it, right here, a freeway that carried about 100,000 vehicles per day. While the bus was in its normal operations over these weekdays, the CO, carbon monoxide sensor, was getting a reading every 3 seconds with a timestamp. We didn't want to use the power, take up the space to put a GPS sensor in the configuration, so we matched the timestamps in the CO, the readings, with the timestamps on the AVL system to get the locations of the readings. We looked at the CO measurements as a function of distance, linear distance from the beginning of the route. We smoothed the data and gridded it so that we had a reading, or at least a data point, every 100 feet along the route for every bus trip. So in this graph, we show by distance, or from the beginning of the trip, or if you want by location, the proportion of times of these 100 trips that a CO reading at that location was above the median reading for the entire trip. And if there was no location-specific effect, then you would expect the probability that a CO reading would be above or below its median to be 0.5. So we could calculate the 95% 5% bounds, proportion bounds. We saw that 60% of our locations had readings outside of these bounds, as opposed to the 10% that you would expect by chance if there was no location-specific effect. And also notably, we saw that the locations with high readings and low readings corresponded to interpretable built environment effects. For example, points A and B, these locations with high readings or high proportion of high readings, were when the bus went under this 100,000 ADT freeway. A was when it was going eastbound at the beginning of its trip, and B was when it was going westbound at the end of its trip. Similarly, the low location readings, the locations with low proportions corresponded to open green spaces on campus with little cross traffic. We did lots of other analyses with the data. Here I just point out two. One, we used some probabilistic analysis based on the empirical data to show that we could have found these high location spots and these low location spots in relatively few days of bus coverage, which would imply that you could move the sensor around or move your bus with the sensor around to be able to cover the entire area. Secondly, we saw that the readings were positively and significantly correlated with traffic volumes, crudely estimated, but that the fit was low, implying other factors were much involved, and therefore the need for sensing rather than just modeling. So in conclusion, even in this campus geography, we saw systematic spatial patterns because of the repeated coverage of these buses. An urban area, we think, would have a lot more spatial variability, but we also saw that we could discover these spatial patterns relatively quickly, so you could cover an urban area by putting it on different routes, sensors on different routes in a small amount of time. In an empirical study like this, first that we know of, there are a lot of future investigations that are warranted, but I'll leave it there and ask you to kindly read the acknowledgements to recognize the many people who made this possible, and I thank you for your attention.
Thank you very much, Mark. Before going to our last presentation, we will have some time left after all the presentations because everybody has been very good at keeping on time. So I invite people at the audience to make questions through the shared document. And after all the presentations are finished, we will ask the presenters to answer those questions. So for the presenters, you can prepare reading at your questions. Okay, and our last presentation today is called Developing a Smart System to Identify Bus Drivers' Drowsiness Caused by Physical or Mental Fatigue by Vahid Al-Bohassanayed and Mohamed Abdoli Eramaki from Ryerson University. Vahid.
Thank you. Can you see my slides?
Yes, we can.
All right.
Can you put it in? Yeah, that's good.
Okay. Okay, good afternoon, everybody. I hope everyone is in best of health. Today's presentation is about the development of a smart system to identify bus drivers' drowsiness caused by physical or mental fatigue. This project is conducted at the School of Occupational and Public Health at Ryerson University under the supervision of Dr. Abdoli. And my name is Vahid, and I will present it for you today. It's interesting to know every day 4 Canadians are killed and 175 are injured in impairment-related crashes, which is caused by drowsiness due to alcohol or cannabis consumptions or related reasons. So our goal in this project is to recognize the driver's drowsiness, especially bus driver's drowsiness, at the earliest stage before they get into drowsy state. There are various methods have been used so far, which is categorized into 2 main categories, including intrusive and non-intrusive techniques. So the non-intrusive techniques are superior than intrusive techniques, but All of them, but none of them have been tested in the real environment, and none of them can continuously collect and analyze the data, which is really important in this case, in this study. Our technology include three main modules. The first one is data collection. We'll use two types of sensor devices. One of them is a headband, and the other one is a torso band that can continuously collect the ECG and EEG biomarkers, which have already been developed. And the next one is the monitoring module, which uses the different types of techniques, including the AI algorithms, to analyze the signals. And the last one is the alarming module that can actually issue the necessary alarms at the earliest stage before the driver gets into drowsy state. We have, like, to test the proposed system, we have considered to conduct three phases. In the first phase, which is under processing, we are waiting to get the approval because we are working with the humans and we need to get the ethics approval before going through the lab experiment. But during the COVID-19 pandemic, we could not actually finalize this part, and we are still waiting to do the lab experiment. But to get the primary results, we have done the pilot study on one subject and collect his data to get the primary results. According to this pilot study, we have asked the participant to drink wine during 1.5 hours, and we got the different signals, his different signals, when he was awake and vigilant, and also when he got into the drowsy state. We got the signal and analyzed the signal in these two status and estimated the related parameters, including the heart rate and the average of the peak amplitude of the ECG signal. As you see in the table, the heart rate was found higher and the peak mean was found less in drowsy status compared to awake status. That shows the successful performance of our algorithm. And in the next stage of this analysis, we have used the R interval and HRD features. The R interval is the time difference between the peak point of the ECG signal. And according to the results of this analysis, we also found the successful performance of our algorithm. So as a conclusion, we have successfully tested our algorithm in the pilot study and collected, but we could collect, continuously collect the data using our devices. And also we have validated our devices, and also we have found we have estimated different features of the ECG signal that indicated the successful results. And this can convey us to the next stage that can make us sure that the other stage can be validated successfully to some extent, actually. So in the next stage, which is the lab experiment, we need to get actually hire about 30 drivers, including the bus drivers, to collect the data and analyze the data, and got their patterns to recognize their drowsy status at the earliest stage. And here is our laboratory. We have the privilege of having well-equipped laboratories and also the high caliber experts in our team at Ryerson University and Yangyang Inc., who is our partner in this study. And we will hope to achieve the final stage of this study as soon as possible. Thank you for your attention, and here is my contact information. If you have any question, I will be happy to answer. Thank you.
Thank you very much. So now we will go through the questions that have been placed in the Google Drive document. Some of the presenters have already answered through the file, but I will ask them to elaborate a little bit more. So Gregory, would you like to comment on the questions you have received?
Yeah, no problem. I was just writing the fourth question answer. there's a lot of talk about what's the similar conditions, how do we sample every trip to compare other drivers. It wasn't an easy task because we have 46 different lines. How do we sample one line? How do we sample based on the hour of the day? So for example, can we sample a trip based operated at 4 p.m. the same way as a trip operated at 11 p.m. or at 7:30 p.m.? What do we do when we change a schedule 4 times a year? Do we wait 3 weeks to build up some historic? So there's a lot of questions that we tried to answer and we couldn't. So we didn't want to overemphasize or overdo the question. So we developed 4 or 5 sampling strategies. So for example, I take the trip that you operate today, I compare it with trips made last week and up to the schedule beginning. Another sampling strategy would take on the trips made in the same day, but the next trips and previous trips. So for example, on Saturday and Sundays, the variation between travel times is less than on weekdays. So for weekdays, we tend to take the same time, so the trip at 7 a.m., and compare it with the trips at 7:30 on Monday, Tuesday, Thursday, and Friday. Then we compare the trip at 7:30 with a trip at 12 o'clock. So we are using these 4 or 5 sampling strategies, and we try to choose the sampling strategy that gives the lowest dissimilarity between observations. And we're going with it this week. Some other question asked me about schedules, specific routes, etc. We don't take into account the schedules. We only look at the operating performance of drivers. So we don't take into account travel times specified by the planning department or the hours that we publish in their website. Another question asked me about riderships. For example, if there's a lot of ridership in one day, can we compare trips made by one trip with no ridership, another trip with a lot of ridership? Usually ridership is pretty similar, but in the case that the ridership is really high, the travel time will be really high too. So in the outlier process, we would tag this trip. So the trip won't go in the sampling process. But we thought about it. We wanted to remove from the travel time the boarding time for each stop to reduce the effect of ridership, but this was too complicated and other constraints also.
Okay. Thank you very much. Now we have some questions for Wenxun Hu. Wenxun, would you like to comment on the questions you received through the...
No problem. So the first question that I got is, what is the location of bus stops at TSP intersections? Are they before or after the intersection? So we have tested our TSP algorithm with and without near-side bus stops, which means we have tested the TSP algorithm with an with a bus stop at the intersection, before the intersection, and also tested with a bus stop after the intersection. And the results showing on the slide is having a bus stop just before the intersection, or say just upstream of the intersection. And the second question that I got is, what is the size of the training data, and which reinforcement learning algorithm did I use? So the size of the training data varies with different settings of the geometry of the intersection. And usually the reinforcement learning models converge after 50,000 steps. That is to say, our training data is around 50,000. However, we can increase the size of the training data and if need. And the reinforcement learning algorithm that we use is an architecture very similar to the to DQN. We do not use a COBNet. Instead, we use a fully connected neural network. And the third question is, I did not understand if applications were done outside from AIMSON on a real intersection. And what's the possibility to insert the algo at the intersection? Okay, so we haven't implemented, we haven't done field implementation. So only trained and tested the TSV algorithm using AIMSON microsimulation. Then our algorithm is very flexible. So even though we provide an optimal and balanced solution for two directions and also for the two different objectives, different transit agencies can alter the weights assigned to different to different directions or to the two objectives. So they can tailor the weights to meet their own needs. And I think, so what is the possibility to insert? It's very likely, I would say, that we can apply this algorithm in the field because we, whenever we get the geometry information of the intersection, we can pre-train the algorithm using the microsimulation software. And then we use the trained model and still turn on training when we implement the algorithm in the field. So we can improve the algorithm when we're feeding the agent with more real world data when it's been implemented in the field. Yeah.
Okay, thank you very much. And we have one hand raised by Taku. Taku, would you like to ask a question? You're now allowed to talk. Perhaps you raised your hand by mistake. Okay, I think it was a mistake. Well, is there any other question? Let me check in the document. Don't see any other questions. Okay, I would like to ask a question to Vahid. All the presentations were very fast, so it was difficult to follow the details. If I heard correctly, you said you give the drivers wine and then you test how did they behave. Was that what I heard? Or?
Yeah, not actually, because we cannot, according to ethics, conditions, we cannot give the drivers alcohol because they are driving actually.
Okay.
That's why we do it like we have set up the experiments to do at home. Because we will ask the participant to do all the procedure at their home, at their earliest, at their convenience, so they can use the recreational level of the alcohol at their home. But we have like set up an accurate and very, very accurate procedures. So we are still waiting for the approval of our ethics application, and we have not gone through the lab experiments because we are still waiting. But we are hopeful to get this approval late in this month. So and then do the next stage, start the next stage.
And if I saw your graphs correctly, there wasn't much difference between the behavior in normal conditions and after drinking some wine. I guess it was not a large amount of it.
Yeah, the signal's shape is changed actually. After somebody like drinks wine and get drowsy, so the signal features could be changed totally, and then you can recognize, okay, the driver or any individual, you know, gets into drowsy states.
Mm-hmm. Okay. So it would be very, very interesting to hear the final results.
It's interesting. We are hopeful to achieve the goal, you know, as soon as possible.
Uh-huh. Okay. Any other question? Anyone else? No? Well, I think we can resume. I will ask all the presenters to activate your image, your video, so we can give a close to the session. Okay, thanks everybody. It has been really a very interesting session. Looking forward to see some more details of these works that, well, some of them are ongoing work. So thank you very much for being here presenting. And very happy that the organizers of these conferences decided to go ahead anyway, no matter the pandemic situation, and that we could hear these presentations today. So thank you very much. And with this, we conclude the session.
Have a good day.